Have you ever really thought about what a measurement means? Today, we're going to dive into the hidden world behind the numbers we use every day. We're talking about precision, uncertainty, and why the real world is, well, never as exact as it seems.
So let's kick things off with a question that seems super simple, but the answer is actually pretty deep. When you see a measurement, say 150 centimeters, is it exactly 150.000 centimeters? The short answer? Nope. Almost never.
And that really gets to the heart of it. Whether we're measuring our height or weighing some fruit at the store, we're not stating a perfectly exact fact. We're giving a close approximation. We're basically just saying the true value is somewhere near that number.
So, this leads us right into the big problem we're tackling today. The problem with treating real-world numbers as if they're perfectly exact. Because in reality, they almost always have this hidden range of possibilities tucked inside them. I mean, just think about the tools we use every single day. Every scale, every ruler, every measuring cup has a limit to its precision. The numbers they give us are just convenient labels for a value that's actually living inside a tiny, invisible zone of uncertainty. Okay, so if everything has this little bit of uncertainty, where's it coming from? Well, the main culprit is a process we all learned back in school: rounding. It's a really useful tool for sure, but it introduces a small, hidden error every single time we use it. Let's see how.
So what is rounding, really? It's just us taking a slightly messy number like 4.6 and swapping it for a cleaner, simpler one nearby, like 5. It makes life way easier, but we do lose a tiny bit of information when we do it.
Okay, let's make this real. Imagine we measure a line and write down 10 centimeters. And we know that measurement was rounded to the nearest centimeter. The big question is, what could the actual, true length of that line be?
And to wrap our heads around that, there's this key idea called absolute error. It's just a fancy name for the gap between the true value and our measurement. And here's the golden rule. When you round to the nearest whole number, the biggest this error can possibly be is half of that unit. So in this case, 0.5 centimeters.
So think about it. If our wiggle room is 0.5 centimeters, it means the true length isn't exactly 10. It could be as low as 9.5 centimeters, because that, of course, would round up to 10. And it could be anything right up to, but not quite touching, 10.5 centimeters, because 10.5 itself would actually round up to 11.
And boom, this is what it looks like in the language of math. The true length is greater than or equal to 9.5, but it has to be strictly less than 10.5. This range right here is that hidden uncertainty we've been talking about, finally made visible.
Okay, so we found this hidden zone of uncertainty. That's cool, but what do we actually do with it in a calculation? That's where these powerful tools called upper and lower bounds come in. They give us a formal way to get a handle on this range.
And the names for these luckily make a ton of sense. The lower bound is the absolute smallest the true value could possibly be. For our line, that was 9.5 centimeters. The upper bound is the limit that the true value can get up to, but never quite reach. For us, that was 10.5 centimeters.
Let's run through another quick one to really nail this down. Say a mass is 4.2 kilograms, and it was measured to 1 decimal place. That means the degree of accuracy is 0.1. So you just take half of that, which is 0.05, you subtract it to get the lower bound, 4.15, and you add it to get the upper bound, 4.25. It's as simple as that.
Okay, now here's where things get really interesting. This is the part that kind of blows my mind. What happens when we start using these numbers in calculations? This is where those tiny, seemingly insignificant errors can suddenly become a very, very big deal. Let's imagine we've got a rectangle measured as 10 centimeters by 6 centimeters, with both numbers rounded to the nearest centimeter. First, we find the bounds for the length and the width, just like we did before. Now, here's the crucial trick. To find the minimum possible area, you multiply the two lower bounds together. And for the maximum possible area, you guessed it, you multiply the two upper bounds.
And just look at this result. The minimum possible area is 52.25 square centimeters, but the maximum is a whopping 68.25. Our simple guess of 60 by 60 is right in there, but the actual range of possibilities is huge. The true area is way less certain than we probably thought.
So what's the big takeaway here? It's massive. A tiny bit of uncertainty in our starting measurements created this giant range of possibilities for our final answer. And this is exactly why understanding error bounds is so critical in fields like engineering, science, or really anything that needs precision.
But, knowing all this doesn't just make you paranoid about numbers. It actually gives you a kind of superpower, the power of estimation. And it's not about being lazy with math. It's about being smart and quickly finding a good enough answer that you know is in the right ballpark.
I mean, why bother getting good at estimating? Well, for one, it's like having a built-in sanity check to see if your answers make sense. It also frees you from needing a calculator for everything and helps you make quick, intelligent decisions on the fly.
All right, let's try one. Off the top of your head, what's 49 times 18? Don't grab a calculator. The key is to not try and work with these slightly awkward numbers.
Instead, what if you just round them to friendlier numbers? 49 is basically 50. 18 is pretty close to 20. And suddenly, the problem is 50 times 20, which is an easy 1,000. That's a fantastic quick estimate, and it's really close to the actual answer of 882.
Okay, how about at Division 1? How would you tackle 402 divided by 8 in your head? Again, 402 isn't a very friendly number to work with.
But what if we just think of it as 400? I mean, it's so close, right? And 400 divided by 8? Hey, I know that one. That's 50. This is called using compatible numbers, and it makes mental division a total breeze.
All right, before we finish up, let's just quickly cover a few common traps people fall into, just so you can sidestep them. First, always remember that rounding to the nearest of anything means your error is half of that unit. Second, don't mix up your bounds. If you want the smallest possible answer, use the smallest inputs. And finally, remember the whole point. If the problem has uncertainty, your final answer should be a range, not just one single number.
So, we've pulled back the curtain on rounding, we've seen the hidden errors it creates, and we've learned how upper and lower bounds help us manage them. The final question now goes out to you. Now that you have this new lens, where are you going to start seeing these zones of uncertainty? In the news, in a recipe, maybe in construction projects? The world is absolutely full of approximations, and now you have the tools to see them clearly.